Britt Holmén. I'm a professor of civil and environmental engineering at the University of Vermont, where I study vehicle emissions, especially tailpipe emissions, and their effects on human health. In today's Sustainable Transportation mini-lecture, I want to take you through some of the basics associated with vehicle emissions. Why should we all care about vehicle emissions? Well, vehicles are still a major source of air pollution, even though since the 1970s we've been regulating the emissions from vehicles. In fact, since that original Clean Air Act, because of the growth in miles that we travel, or vehicle miles traveled each year, we've still got a significant vehicle contribution to ambient air quality. Air pollution, of course, affects human health in many adverse ways. We're all familiar with asthma attacks increasing, but we may not be aware that air pollution has also been associated with cancer, and now we know premature death and even neurological effects. More vulnerable groups, such as children and the elderly, are of special concern in our protection of their health. Another aspect of air pollution that we often forget about are the human welfare or environmental effects. These occur at two scales. Regionally, it might involve visibility. When you go to the Grand Canyon, you do not want your experience there to be diminished because of airborne particles and haze issues. Similarly, ozone, a critical air pollutant, affects the yields that we get from crops and the growth of our forests. At the global scale, vehicle-derived emissions of greenhouse gases, of course, contribute adversely to climate change. So what I want you to take away from today's lecture: one, be able to summarize the air pollutants related to motor vehicles, be able to distinguish three different categories of pollutants that we care about, distinguish between emission standards and ambient standards, the two different types of regulations associated with air pollution, and to explain the trends that we're seeing over time in ambient air, in vehicle emissions, as well as fuel economy. We'll discuss factors affecting emissions from vehicles. These include: how does an internal combustion engine work? How do we measure what's actually coming out of a vehicle? And then what are the contributions to the magnitude of vehicle emissions associated with how a driver drives and the kind of technology that we have available to us? Finally, we'll conclude with a discussion of how fuel economy and emissions are related. So let's take a look at what's been going on in ambient air. Here's a graph provided by the EPA since the latest Clean Air Act amendments in 1990. So on the x-axis is time, and on the y-axis is the percent of the pollution change in ambient concentration relative to the ambient standard in each year. So the middle of the graph would mean your concentration was right at the ambient air quality standard, or the point at which, the concentration at which we start to see adverse human health effects. All of these lines have negative slopes. That's a very good thing. That means that we have been decreasing our emissions and therefore our measured ambient concentrations. This occurs because we chiefly have implemented controls on the two major types of air pollution sources. On the left is shown a smokestack from, say, a coal-fired power plant. Those are stationary sources or point sources. A little more difficult to control because they don't have as constant behavior over time are the mobile sources. Our interest today is on on-road sources, but there's another category known as non-road sources that would include construction and agricultural vehicles. They also contribute to what we measure in the ambient air. What are we actually measuring? Well, as shown on the graph, there are 6 pollutants that we call the criteria pollutants. Criteria means that early in the 1960s, there was found to be an association between a certain concentration of these pollutants and an adverse human health effect. And the documents were called criteria documents, so the name continues to this day. Carbon monoxide, sulfur dioxide, nitrogen dioxide, lead, particulate matter, which comes in 2 different sizes, and ozone. Those are the pollutants that were shown on the previous slide. The NAAQS, or the National Ambient Air Quality Standards, then refer to concentrations in ambient air that cannot be exceeded. The primary NAAQS are the ones associated with protecting public health, not welfare, with an adequate margin of safety, according to the Clean Air Act. So every county in the United States has been identified based on real-world ambient measurements to be an attainment zone or a non-attainment zone. And this map of the U.S. shows that in 2017, the number of areas and with colors that were non-attainment areas. To give you an idea of how much of an improvement we've had, the next slide will be the same graph, but for 2014, 3 years earlier. So compare the number of colored areas. Okay, you can see that there was an improvement over time. The colors correspond to the number of pollutants that were in non-attainment or exceeding the national ambient standard. You'll also note the majority of these areas on the graph correspond to urban areas. So urban areas have more dense population centers and more infrastructure, therefore obviously higher pollutants. So it's not a, doesn't take a rocket scientist to see those relationships, although there are some areas like in Florida where we don't see exceedance of the standards, and that might be due to the weather conditions that occur there, helping to dilute any emissions. Now let's think about what's this got to do with transportation. Well, EPA can also look at all the different types of sources, and we can categorize those into how much do they contribute to our total burden, okay? So you can see here all the pie charts for different pollutants. Anywhere you see a gray piece of the pie, that's the transportation contribution. So obviously, for carbon monoxide and NOx, vehicles are a major source. For VOCs, or volatile organic carbon, they're also another source. The other pollutants are chiefly emitted by other types of sources, mostly stationary sources. There are two more types of vehicle emissions that we need to be concerned about that are not part of that ambient or NAAQS inventory that we just spoke about. And these are mobile source air toxics, or MSATs. These cause even more adverse health effects: cancer, birth defects. Chiefly, these are a list of toxic hydrocarbon gases. You've probably heard of benzene. It's a component of gasoline. In the air, it is an air toxic. You've also certainly heard of formaldehyde from your middle school science class. Ultrafine particles, not currently regulated in the United States, but they are regulated in the European Union, could also be considered a mobile source air toxic because they're known to cause cancer. The other category, the third category, is greenhouse gases. These affect the Earth's radiation balance, have an effect on climate change, and the chief gases are CO2, methane, and nitrous oxide. Now, we've talked about air pollution sources in terms of the type of source, the type of human activity that's taking place, but there's other way to categorize these sources. Primary pollutants are those that are directly emitted. So what comes out your tailpipe, for example, is a primary air pollution source. Notice that these include all of the chemicals on the criteria pollutant list except for ozone. Ozone is in a special class and is known as a secondary pollutant because it is formed by reaction in the atmosphere. So as shown on this next slide, we're talking when we say smog or ground level ozone, also known as tropospheric ozone, we're talking about a photochemical reaction that is dependent on light. And typically we see smog formation and smog alerts in the summer because chemical reactions in the atmosphere go faster under warmer temperatures in the summer. So the simplified chemical reaction that I've shown says VOC plus NOx plus that key ingredient, sunlight, reacts to produce ozone and a bunch of other secondary pollutants. Key to our discussion here about vehicle emissions is the fact that the VOC and NOx, the two precursor gases, are critical to the formation of ozone, are primarily emitted by motor vehicles. All right, here's your typical car. There are two types of emissions from your vehicle. One, the one you most often think about, is tailpipe emissions. There's the list of what comes out your tailpipe. The other type of emissions that we often forget about are known as evaporative emissions. These are associated with the fuel. Your operations around your car when you're filling it up with gasoline are responsible for these hydrocarbon emissions. Also, when your car is just sitting out in the parking lot on a hot day, it may be emitting hydrocarbons. Some of those hydrocarbons, again, might be falling into the air toxic category. Some of the effects are shown here then, just as a reminder. Hydrocarbons and NOx contribute to ozone formation. Carbon dioxide, we care about the emissions of CO2 because it's a greenhouse gas. And particulate matter, we care about it because of it's a directly emitted, may form or contribute to haze, and is also a result of secondary reactions. So let's talk about what goes on to create these pollutants when you're burning fossil fuel in your car. So combustion is just a reaction at high temperature and pressure between air, the oxidant, and your fuel, either gasoline or diesel. Under ideal combustion conditions, which don't occur very often, you end up with relatively benign, and I say relatively benign because of course there's CO2, the greenhouse gas that we do have to worry about, but you get relatively benign products as shown by the chemical equations: CO2, water, and nitrogen, which is a component of the atmosphere. Okay? But as I said, we rarely have ideal combustion conditions, which means we rarely have a sufficient amount of oxygen from the air to combust all of the fuel, especially when we're operating engines in a transient state. So these incomplete combustion conditions are what constantly go on in the real world and contribute to the formation of pollutants out of your engine. These pollutants are carbon monoxide, a wider range of hydrocarbons, some of which might be mobile source air toxics, nitric oxide or nitrogen monoxide, not to be confused with nitrous oxide, the greenhouse gas, and finally particulate matter. Again, hydrocarbons are a mixture of hundreds of individual compounds. They're so complex, we typically measure them as a group. Exhaust particles are another, not a single composition. They're a complex mixture of different things. And it turns out that the health effects, to some extent, are a function of the particle size. Shown here is a typical diesel exhaust particle size distributions. On the x-axis is the size of the particle on a log scale, diameter in microns, and on the y, a relative concentration scale. I want you to look at the blue line. The blue line shows the fraction of particles that you inhale that are actually deposited in the alveolar regions of your lung. That's the deepest regions of your lung. Okay? If you look at the graph for the zone labeled particles of designated as ultrafine particles, those smaller than 100 nanometers in diameter, you see that 70% of particles, of ultrafine particles that you breathe in, stay with your lung. So that means whatever is on those particles can therefore get into your bloodstream, and now we know even can cross the blood-brain barrier for some of the smaller particles. So we care about particle size as well as the quantity of particles that are emitted. One more thing on this graph. The big peak on the left-hand side, the nuclei mode, that's how we would measure particles if we were counting the number as opposed to weighing the mass of particles. The middle, or accumulation mode, shows the mass weighting of particles, which shifts towards the larger particle sizes. Because very small particles, there's lots of them, but they don't have very much mass. So we typically drive on the road these days two types of vehicles, one with a gasoline spark ignition engine, and the other a diesel engine with a compression ignition engine. It turns out that not only the fuel composition, but how that fuel is burned in the engine affects what comes out the tailpipe. So in a gasoline SI engine, fuel and air are pre-mixed, and then in the upper left of this graph, an intake valve would open. The combustion reaction would be initiated by an electrical discharge from the spark plug. And then the piston goes down, turns the crank, your car moves. For a diesel engine, on the other hand, fuel is directly injected into the engine. This leads to different reaction products, chiefly particulate matter and NOx as being the pollutants of concern for diesel engines. So we can draw a little cartoon that characterizes these differences. Notice that the size of the circles is larger for NOx and soot on the diesel engine side compared to carbon monoxide, hydrocarbons, and a little bit of NOx on the gasoline side. The Clean Air Act is full of emission standards for different sources. So for vehicles, you'll note here, this is the regulatory amount of carbon monoxide, hydrocarbons, or NOx that's allowed to be emitted by new vehicles of different model years from 1968 to 2004, as represented in the Clean Air Act. So if you wanted to try and estimate the emissions from a vehicle in terms of the grams of pollutant per mile driven, you could go to the Code of Federal Regulations, look up the value by model year in the emission standards. Alternatively, to figure out how much is being emitted from a car, you might take it into a lab. And this is how these regulatory measurements are made. So manufacturers have to subject their car to certain federal test procedures. As shown here, you basically put your car on an instrument known as a dynamometer. That's like a treadmill for your car. The exhaust is mixed with dilution air, sent to a bunch of analytical instruments to quantify what's the concentration, and then if you know how far the car drove during that test period, you could convert the total mass of pollutant collected, say in a bag, to divide it by the miles driven, and you'll get the emission factor. We have a bunch of different drive cycles, regulatory drive cycles, that are used to estimate the overall emissions from a vehicle and whether or not it will meet the standard. So a drive cycle is just a speed time trace, how fast the car will go at a different second in the drive cycle. And on the treadmill, the treadmill driver is actually trying to follow the trace quite closely. The Federal Test Procedure, or the FTP drive cycle, is the one that is used to certify compliance. In addition, in the last few years, we've discovered that the lab test cycle does not do a good job mimicking the types of emissions that we see on the road. So what this means is EPA has gone to a lot of trouble to try to develop different drive cycles, as shown here by the blue line and the orange line or yellow line, different test procedures. For example, the US 06 cycle is intended to represent more aggressive driving behavior, and the SC03 cycle is to account for use of air conditioners that contribute to load on the engine and therefore affect emissions. So if we just sum up the different factors that affect real-world emissions, these include a whole host of things on the left-hand side that are related to essentially the technology. What type of vehicle are you driving? How old is it? How much does it weigh? If it weighs more, it obviously takes more fuel to move it a certain distance. What type of engine does it have? Is it going to produce mostly PM or mostly carbon monoxide? What are its aerodynamics in terms of its body design? What's the composition of the fuel? Is it pure diesel, or is it diesel mixed with a biofuel? Same for gasoline. What kinds of emission control technology is on the tailpipe? And finally, what % of electrification? Is it a hybrid vehicle, or is it a pure internal combustion vehicle? On the right-hand side, those are factors that affect emissions associated with sort of environmental effects. What's the road grade? If you're going up a hill, obviously, you would have more emissions because you would consume more fuel than if you're going downhill. How do you drive? Or do you drive like a grandma, or do you drive like a jackrabbit? So your speed profile, your acceleration profile, all of those things affect how much you're going to emit and how much fuel you'll consume. And finally, ambient temperature. If the temperature is really cold, it takes a lot longer for the emissions control equipment on the car to heat up and therefore be operating and controlling the emissions. And similarly for ambient humidity. On really hot and humid days, you're probably using your air conditioner, which is contributing to the amount of fuel and therefore the amount of emissions. So let's take a look at one of these factors, speed. It's the easiest for us to all understand. I said two factors affect the technology you're driving as well as sort of how you're driving. So let's just take a look at 35 miles per hour. You'll see here that for carbon monoxide, the emissions are really low for diesel. That's because of the type of engine and the combustion process, as we said before. CO is really low under lean operating conditions. For the blue graph, which is a passenger car, emissions are higher, but lower than that for a light-duty truck. So like a pickup truck, your emissions are going to be higher than they are for a passenger automobile. Next, look to the left-hand side, where there's a large increase for all three plots at really low speed. And that's representative of the cold start emissions, which are always many orders of magnitude higher than your stabilized emissions or stabilized running emissions once your engine and catalytic converter have heated up. We try to describe in vehicle emissions models, we try to describe how a person drives in terms of both the speed and this other parameter known as the vehicle-specific power. So as shown here, there are many forces operating against the vehicle as you try to move it. Rolling resistance of the tires, aerodynamic drag, road grade that we mentioned before, and then just kinetic energy, how fast you're going. Okay? So we calculate VSP along with general speed bins, and we can estimate for a given vehicle type what would the grams per mile emissions be. The model that does this in the United States is known as MOVES, the Motor Vehicle Emissions Simulator. All right, let's take a look at greenhouse gas emissions from vehicles. Well, we know that transportation CO2 emissions have increased about 20% since 1990 to 2018, the latest data currently available. And of that, light-duty CO2 is up 14%, chiefly due to this fact that we've driven 46% more than we used to in 1990. What's causing this? Well, there's more people, there's more cars, there's sometimes more distances to go because of our urban landscapes. And finally, low fuel prices have made it relatively cheap for us to drive our vehicles. If you look at the bottom half of this slide, you'll see that passenger cars and light-duty trucks, those that we use for everyday commuting, are responsible for about 50% of the CO2 emissions. So clearly, we've got to think about our vehicle contributions to greenhouse gases. One other way you can think about that is doing a calculation of what your per mile CO2 tailpipe emissions would be. You need two factors. One, you need your fuel carbon content, and two, you need to know your vehicle's fuel economy. Okay? So the two EPA numerical values for carbon content are 88.7 grams of CO2 per every gallon of combusted for gasoline, and the corresponding higher number, 10,180 grams of CO2 per gallon for diesel, because it's a higher carbon fuel, but diesel engines are more efficient, so it's kind of a wash in the end. And then to do the calculation shown in the example for a gasoline vehicle, you end up with about 411 grams of CO2 for every mile you've gone if you have a fuel economy of about 21 miles per gallon. How have we been doing as a fleet in terms of our fuel economy trends? This graph from the latest automotive trends report from EPA shows that our fuel economy has been improving since 2004. Prior to that, it was pretty stagnant or even going down. And part of the reason for that is we've been choosing larger, heavier vehicles. So the green line here is, again, the same real-world fuel economy that we saw in the last graph, and then additional plots to show the weight of the vehicles, which started to level off in the early 2000s, mid-2000s, but that we still want to drive those cars that are, those vehicles that are high horsepower. And that means we're basically driving SUVs and trucks. So as shown here on the left-hand side, the colorful graph is the production of vehicles, what the manufacturers are providing for us, and then the right center is showing the fuel economy profiles for cars on the top and trucks on the bottom, and you can easily see that a truck chassis type vehicle always has a higher fuel consumption than a car. Now, manufacturers are trying to meet new Obama-era fuel economy regulations. They're doing this with a number of fuel-saving approaches, the approach being taken by different manufacturers. The manufacturers are shown across the top, and the different types of technologies are shown on the left-hand side. Everything from electrification to using start-stop technology is a popular one these days with a wide range of manufacturers. So getting towards our conclusions here, how can we think about reducing tailpipe emissions? Well, I hope I've convinced you that one surefire way to reduce tailpipe emissions is to stop driving. Find ways that you can get from point A to point B without taking your car. Maybe it's the bus, which will be more efficient. Maybe you can telecommute some days. We can also think about going towards more energy efficient technologies, plug-in and hybrids, electric vehicles, fuel cell vehicles. We might have different energy sources, so low carbon fuels, the implementation of those standards seems to be taking off after California's lead. We might look towards biofuels and hydrogen as alternative approaches, especially places where we can have renewable electricity sources for electric vehicles. So we really need to change our use of vehicles, our behavior, as well as the whole transportation system if we want to achieve meaningful reductions in tailpipe emissions. So in summary, I hope I've given you a good overview today of what's coming out your tailpipe, what's happening when you're driving your car, that you've got an understanding that our trends in ambient air in response to the National Ambient Air Quality Standards has typically been good, but most of the benefits accrued so far have been because of stationary sources. The transportation sources, we're still running on fossil fuels, and therefore we're still contributing to many of the criteria pollutant, greenhouse gas, and other problems. In terms of the vehicle emissions inventory, therefore, we have to say not so good. And in terms of air toxic and ozone, we're only starting to sort of touch the surface here so far, especially for air toxics. It should go without saying that you should stay out of the way of whatever's coming out of tailpipe to the extent possible as you go about your day and your work. And finally, on fuel economy, as we're waiting for the new standards to kick in, it'll be interesting to see what manufacturers provide us for high fuel economy vehicles, and then what will the consumer actually purchase. So those two things together will dictate where we go in terms of the larger global scale greenhouse gas emissions and the associated more local scale production of criteria, air toxics, and secondary pollutants like ozone. So thank you for your attention. I'd like to thank my research group at the University of Vermont and the students who participated in my classes over the years, as well as a number of funding sources that have supported my work on vehicle emissions and their health effects. If you have any questions, feel free to email me. Thanks again.